One moment. So I'm ready. Okay. So hello, I'm sorry that I'm late. I'm Paula, and I'm finishing my PhD. Today I will present a method to estimate and predict the regional record probabilities at the interannual scale from weather station measurements. And this is a joint work with Philippe Nabos, Philippe Tao, and Julian Worms that are my supervisors. So, oh, no, no. So I'll go like this because I'm sorry. In the last decade, there has been a strong increase in high temperature record-breaking events. And these events have a lot of media attention because they are unprecedented. In addition to being extreme, they break the limit of what was possible so far. And previous studies suggest that the amount of record-breaking events is increasing, and that this increase depends on the rate of warming. In addition to that, we know that there are stronger regional signatures in how the temperature distribution deviates from climatology. So in this context, the objective of the work I'll present today is to provide a tool that allows us to investigate how the current global warming trend affects records at a local scale. So first of all, a record is a value that is larger, that's higher than all values in a reference period. And this reference period is often constituted of all previous entries. So for example, here, we have the yearly maxima of daily maxima temperature measured at the weather station Paris-Montsouris in Paris from 1960 to 2022. And we have here 80 records that are represented by the green dots. So this is the temporal scale we are interested in, yearly maxima of climate variables observed at a daily scale. This yearly maxima captures the most extreme conditions observed in a single day, and a year is said to be a record if at least one of its daily variables is a record. So the specific event we will be interested in studying are records over a region. Here, for example, we have 5 time series of yearly maxima of daily maxima temperature measured around Paris, again from 1960 to 2022. And now the green dots represent the records at Paris over this 5 station region. So in mathematical terms, this is the event, this is how we define the event record over a given region. So here, S is the ensembles of sites, or in our case, as we application example, we have weather stations. SO will be our site of interest, that in the previous example was the station Paris-Montsouris. Capital T, it's the extent of period, like the length of historical observations. And YTS will be the random variables associated to time T and station site S. So here I will illustrate how I will present the example where we will test our method. So here we have, we take 3 regions of 5 stations in different parts of France. And in blue, we have the Brittany region, in green, the Paris region, and in the south of France, in the south of France region in red. And these regions, we will consider them homogeneous and we'll consider that the stations are homogeneous between them inside the regions by climatological difference between regions, in different regions. And here, the light points represent the interest station, that was SO. So here we see the panels, the time series of the yearly maxima of daily maxima temperature measured at each one of these points. And what we see here is that these time series are, one, highly correlated, and second, they have some trend that might not necessarily be linear. So the question that we will ask ourselves is what is the probability at a given site of observing a record over a region in the upcoming year? For example, in this case, the upcoming year is 2023, and our station of interest will be Paris. So this is the inferential objective, that is the probability of the event that I defined it earlier. So in the case where, if we put ourselves in the simplest case, where all of our random variables are identically independent and identically distributed, the probability of observing a record is 1 over the number of variables that are being compared. Here, as I said, T is the number of previous observations of the length extent, in this case, 1960 to 2022, and S, the number of sites in the region. But we know that we are not in the IID case. So there are some statistical models that go beyond the IID model for record probabilities. But these models are not adapted to all particular problem of interest. Non-stationarity is usually handled with linear trends, and there are no models that can handle multivariate, highly correlated time series. So to our knowledge, there are, at this moment, no model that can forecast the record probabilities in a non-linear multivariate context. So to build our model, now we present what we do to find our model for this probability. So we use the first thing we do is that we use extreme value theory. So extreme value theory, the convergent principle that we all know is that the block maxima converge to a GV distribution. In this case, the block are 365 years, and the maxima is the yearly maxima. So the GV are defined by different parameters: the scale, the position, and the shape parameter. And the shape parameter defines the support of the distribution. Here we are working with temperature. Temperature is usually modeled with a negative shape parameter. This means that we'll have distributions with an upper bound. So for build our model, we have some assumptions. The first assumption is that we have GV distribution. And the second assumption is that we have some similarities among this GV distribution. We will say that the region is homogeneous, and we define homogeneous as a region in which the tail index, the shape parameter, and the support of our marginals are constant in time and space. As a third assumption, and this assumption it's justified in that we take neighboring points, and as we saw in the time series, they take like the same value range. The third assumption is a commonly used assumption that yearly maxima are independent time series. And the fourth assumption is that for a given time, the spatial random vector follows a mixed table multivariate distribution with invariant dependence, in this case, spatial dependence. Now we will denote by V. So the max table multivariate distribution is a natural extension of extreme value theory to the multivariate case. So we'll say that the composite-wise maximum converge to the multivariate extreme value distribution. And in the case of unifurcate marginals, but without loss of generalization, the cumulative distribution function of this multivariate vector is defined by this dependent function V. And this function has one good property, that it is that this is of order -1. So these are the 4 assumptions that we have for our model, and we see that these assumptions allow us to capture non-linearities in space and time, and to integrate a strong spatial dependence. So with all of these assumptions, we build this model. We find this equation in which the record probability at site SO in the upcoming year depends of 2 components: the dependence function, and that's one component, and the second are these parameters U that characterize the parameter change, the relative parameter change among our marginals. So here it's a definition of these parameters U. And we see that here in the top we have the scale parameters of a random variable as site SO and time t+1. And here in the bottom, one of the scale parameters of one of the random variables in the reference period. So this is like the general definition of this of the model. But if we take a simple case, for example, if we take the case where we have the same margins and marginals in time and space, this means that there's no warming trend for the warming trend. This equation simplifies to 1 over 1 plus t multiplied by a factor alpha. And this factor alpha is in fact the extremal coefficient that measures the dependence of our multivariate vector. This parameter alpha goes between S and 1 by definition. It takes S, that is the number of, this is the spatial dimension, the number of sites in a region. This case represents the IID case, where we don't have a dependence, and it takes the value 1 when we have perfect dependence. So we can see that in the case of independence, we go back to the base model where the record probability is 1 over the number of variables that we are comparing. And an important thing to note is that when max like as the extremal parameter value goes down, when the dependence go up, record probability increases when the dependence increases. So for example, here there's a toy illustration example where I take a region of dimension 5. We have a 5 time series with the same time varying marginals, and a logistic dependent function of parameter 0.3. This and we take the record probability of one of the variables over the region at each time step. So here, tau will be the next time step, the next time. And we will compare this probability with the IID case in black and with a more simple case where there is no trend. So all marginals are the same in space and time, but there's still a logistic dependence. So obviously that both of the components, trend and dependence, affect record probability. Here we can see better here in the plot at the right, when we see the ratio between record probability and the IID case. When there's a trend, the divergence continues to increase, but even when there's no trend, we have a difference, and this difference is constant, like it's the record probability from an IID is translated. So this is like how our model behaves. And now how we estimate, how we did the inference of this probability. So what we will do is non-parametric inference technique. So we can capture all non-linear trends in the space and time. And we estimate the dependence function of one side, and then the parameters, the U that characterize the marginal behavior, and then we plug them into a fine record probability. But as we do not have the observation at the upcoming year, what we'll do is that we'll estimate this probability at each previous time step, and from this time series of probabilities, we'll forecast the one of the upcoming year. So for the estimation of the dependence function, we will use the Madogram approach, which is an approach that makes the link between the spatial dependence and extreme value theory. The L1 distance between the mean of our standardized random variables and its maxima. Here the F are the cumulative distribution function of variable t at time s. And as we need this cumulative distribution function and we don't want to really estimate these parameters, we use a kernel method, a non-parametric kernel method. So this is the first component. For the second component, thanks to our assumptions, this random variable, that is the cumulative distribution function of one random variable yts applied to another random variable, but the one that we are interested in, follows a beta distribution of parameter u. That is the parameters that we want to estimate. So we use this property to estimate the parameters u through the expected value of the beta distribution. So here again, we use a double kernel method where we estimate non-parametrically the cumulative distribution function and then the expected value. So now we have all, after these two steps, we have all we have estimated all parameters and the dependent function. And the third step is that we do a second-order exponential smoothing, so we can capture nonlinear trends to the upcoming year. So now I will present the results of this approach on the method, on the illustration example that I presented at the beginning. These were the time series. What's important to see here is that, for example, we will have different results for each region, depending on the trend and the correlation between time series. So here we have the same color code. In green, in blue, we have record probability at Brest over the Brittany region. In green, record probability at Paris-Montsouris over the Paris region. And in red, record probability at Salon de Provence over the south of France region. And the dot at the end is the forecast. And the black curve is the IID 1 over the number of variables that are being compared. So we see that we are all able, just with this 60 years period, we're able to estimate the probability and that we find results that are different than an IID case. Here the probabilities are very small, so to see really what is this change, we look at the ratio. For example, here in Paris-Montsouris, for 2023, the forecast is 8 times higher. The one that will have been forecast via IID model. And this means that records that were supposed to be very rare are becoming more probable. An important feature and an important thing that we notice is that spatial dependence has a strong effect. For example, in here, I plot the ratio between our model, P tau SO, over a more simple model where we capture the trend, but we assume independence, spatial independence. So here what's important to see is that this probability is, if we don't take into account the spatial dependence, the probability is underestimated. And this underestimation depends on the correlation between among the region. For example, here in Paris, where time series were very correlated, this factor is of 3. So these are the results of this example. Now, in summary, what I presented is that we developed a method that is able to estimate forecast in the coming year record probability in a non-stationary multivariate context, and that we don't need to estimate the behavior parameters. So we need less data, that we can infer things with less data. And we have a non-parameter max level structure, so we take account also spatial linearities. And also, this the example I show is very there's no optimization, so the implementation is very fast. So in terms of climatological results, we see that it's possible to forecast that regional dependence is spatial dependence is important, and that records that should be very rare are becoming significant. So now, as future work, the idea is to, first of all, have some confidence intervals, because at this moment, like, we have the forecast, but no confidence intervals. And also, a thing that we note is that when we take a region, record probability does not depend that much on how many points we take, how many stations, the dimension of the region. So this can be, but maybe this probability could, like, help understand, like, see an index for records. So thank you. That was my presentation. I hope that you have a good. I'm happy to answer some questions.
Thank you, Paula. Please, everyone, feel free to ask questions in the chat or directly to the discussion with your micro open. Yes, sir.
Hi, Paula. Thanks very much. That was really exciting. And I learned a lot. So I had a very naive question. So in your initial graphs where you gave an example how this looks around Paris, you were using absolute temperatures. And I wasn't quite sure, are you defining the records as overall records? And if so, I mean, do you do this in an anomaly space? Or, I mean, what if you would include a nearby mountain that has fundamentally much lower temperature and would never reach that record? And the second question would be, could you apply the same framework of making statements about the probability over the whole of France, where some nearby stations are highly correlated, but then others are probably have a much lower correlation, spatial correlation?
So your third question, I think both of
So the first one is if you had another dashed curve here for Brittany, which was 10 degrees lower, say, right? And I wasn't quite sure how you define your record in the spatial network. So if one, I mean, that would have a zero probability of reaching the overall record across the whole region, if I understand it.
Yes, but that's correct. In fact, as we don't need, like, we model the relative behavior between random variables, we don't really need to observe the records to estimate record probability. And also, one of the assumptions is that the support is the same. So if we have a time series that is really different from the others, that the setup will not be will not follow the assumptions.
Okay, I see.
And for the second one, is the same answer. Like, we have some assumptions, and if we take 1 point of France with respect to all France, it's unlikely that our assumptions are followed.
Okay, thanks. But that makes a lot of sense. Maybe if I'm already, can I ask a last one? Is could you also account for temporal autocorrelation if that were, I don't think that exists for maximum temperature in a given of annual maxima, but maybe if you would look at monthly maxima, you would have some temporal autocorrelation.
Yes, indeed, like, the model have the assumption of independence, but if we want correlation, like, it will be necessary to develop another model, a more complex model. So in the current moment now, it's not possible. But if we continue further development on the theory, maybe it's possible, but it's not as straightforward. Like we have to think about it.
Thank you.
Any other question? Oh, maybe Paula, you want to add something regarding your presentation? I don't know.
Just like one thing that, because maybe you know more about temperature climatology than me. So what I was thinking about is in which zones, on what in what space times it will be interesting to apply this model. For example, here we take 5 regions, but what will be the extent that will be interesting to study in order to understand something about climate change? I don't know if you know something about it.
I mean, if I may, I mean, I think it's a super exciting approach anyway, because a lot of people, I mean, the records are often making news, right? They're often reported in the media, and then because they're reported all the time, and they're basically for different, they could be for different months, they could be for different stations, then people get an impression that it is very normal to get records because every day they read in the media that there was a record somewhere. And actually such an approach that at least over a limited area make such a comparison is very useful. And then I think if to meet your assumption, basically you would need to find regions where you have relatively homogeneous behavior of the stations, if I understand correctly. So and that's that is clearly places where you don't have a lot of terrain, or maybe close to the coast or something like this. But I think it would be actually interesting also to compare urban and rural station, for instance, or something along these lines. But I think it's a useful approach. I've been wondering whether you could actually apply the approach rather than for absolute temperature, always express things as anomalies, and then actually compare stations over larger regions, because usually I think you would maybe I need to read the paper, but well, you could probably easily have, I mean, the anomalies, if you remove the mean, are much stronger spatially correlated than the absolute values. That makes sense.
Thank you.
Okay. Well, thank you, everybody. If there is no other question, we can wrap up here. Paula, if you have anything to say before we say goodbye, please be welcome.
No, it's good for me. Thank you.
Okay. So thank you, everybody. And I hope I see you next week for the last webinar of the year. Thank you very much, Paula, and thank you, everyone.